Okay, so thank you for Dee for the introduction. Hi everyone, my name is Zhiyan Ding. I'm a postdoc in UC Berkeley. Today I'm going to talk about optimized signal fitting for quantum phase estimation on an early fault-tolerant quantum computer. So pretty long title. Okay, so this is a joint work with my colleague Yurong Dong, who is a graduate student in UC Berkeley, and my postdoc mentor, Professor Lin, and also Yutong from Caltech. Okay, so basically, in this talk, I will focus on the quantum phase estimation problem, which is a problem I will discuss, and the method we will use is something called the optimized signal fitting. So basically, it's a method, and we mainly want to consider to solve this problem on the early fault-tolerant quantum computer. So it's some kind of device, and it will give us some constraint. Okay, and in this talk, I will talk about four different parts. So first, I will introduce the main problem. So basically, the phase estimation problem. Then I will try to propose our method, which is called QCELS, and some informal result and informal proof. Then I will show that the QCELS is very robust, and we can easily extend this QCELS to other applications, and finally some quick conclusion. Okay, so here for convenience. In the first part of my talk, I will mainly focus on this ground state energy estimation problem. This is a very popular topic in quantum computing. Essentially, we have a Hamiltonian H, which is a very large Hamiltonian. We want to estimate its smallest eigenvalue, lambda 0, and we often call it the ground state energy. And for simplicity, I assume my lambda 0 belongs to minus pi to pi, and I also assume its smallest eigenvalue is phi 0, which is normalized. Okay, so this is a very standard problem setup. Okay, so then to estimate this ground state energy, I must assume some input model. So first, I assume I have some initial state, which is also a normalized state. In particular, in our talk, we mainly care about the overlap between this initial state and the ground state. I assume it equals to P0, essentially equals to this inner product square. Okay, and for the input model, I need to assume some quantum oracle. So here, because we need to estimate the ground state energy of H, we must need some information from H, and to make this friendly to applied mathematician, you can basically imagine that we have a quantum computer, and essentially we put the Hadamard test circuit in this quantum computer, but it's not very important in my talk. Basically, you can understand it as for any given t belongs to real number, you put it into the quantum computer, it can generate a random number ct, which equals to plus minus 1 plus minus 1i. But the important properties for this random number ct is if we take the expectation of ct, it can be written into the following Fourier summation. Okay, so essentially you can understand it as a multiple signal, and this pk is the overlap between the initial state and the other eigenstate, and this lambda k is other eigenvalue. Okay, then we want to, based on this two input model, to estimate lambda 0. So a general way to design the algorithm also mentioned by Lexi and Peter. So basically, we can try to find a proper way to choose our set of time points Tn. Then we put it into the quantum computer, generate a bunch of random signal. Then we try to put this random signal into this classical computer and do some post-processing process. Then we hope we can get a good estimation to lambda 0. So basically, I think a lot of algorithms can fit this framework. Okay, then then basically now when we consider under this framework, when we consider how to design a good algorithm, we only need to focus on how to pick this Tn and how to choose our post-processing process. So it's essentially kind of a classical problem. Okay. So then here in my talk, how do I quantify the complexity? So here I only care about the complexities in the quantum computer part. And in this talk, I mainly care about these two parts. The first thing is called the maximum running time, meaning the max of the absolute value of Tn. So why we care about this quantity? Essentially because for any Pn, after you put it into the quantum computer, actually in this quantum circuit, you need to do this Hadamard. So you need to do this Hamiltonian simulation. If you choose a large Tn, then you need to do this Hamiltonian simulation for a long time. So intuitively, this means that your circuit depth will be deep, and you need to build a very large quantum computer to fit it. Okay, so basically, we want to reduce this maximum running time to make sure that our algorithm can be run on a small quantum computer. Okay, and the second thing, the second complexity is a more common one called the total running time. So basically, for each Tn, because we need to run the Hamiltonian simulation, so intuitively we need to wait some time for this Hamiltonian simulation to finish. So essentially, by calculating the total running time, it can tell us how long we need to run our algorithm. Okay. Yeah. Okay. So and question here. Okay. So yeah. So then in my talk, I will mainly focus on reducing the maximum running time because we are focusing on the early fault-tolerant quantum computer. One way to understand it is we only have a small quantum computer and we can only put short circuit depths. So basically, I want to reduce this maximum running time. So yeah, so there are a lot of classical results for the quantum phase estimation. So here I gave two particular examples. So here to get epsilon accuracy for the ground state energy. So one method is called the Hadamard test. So we need to to run the Hadamard test, we need to ensure that this initial overlap equals to 1, meaning that my initial state is exactly the ground state. Okay. So the advantage of a Hadamard test is I can keep this maximum running time to be order 1. However, the disadvantage is the total running time is 1 over epsilon square. So it's not optimal. Then later people can deal. People have developed a lot of different methods to achieve this optimal scaling in the total running time, such as QPE, QETO, and all other methods. And this optimal scaling is often called the Heisenberg limited scaling. Okay. But here, in my talk, I want to mention that previously, for all of this method, they often use this Tmax is at least larger than pi over epsilon. And in the first part of my talk, my goal is to try to reduce this number. Okay. So basically, our method can achieve that if you have a relative good initial overlap, meaning that this P0 is larger than 0.5, then we can find a method such that its Tmax is much smaller than pi over epsilon, and on the same time we still have the Heisenberg limited scaling. Okay, so yeah, so let's look at the informal theorem. So essentially, assume this P0 is larger than 0.5. We can find an algorithm. We call it a QCELS, such that with high probability we can output. So we can achieve this epsilon accuracy with this Tmax, which is order 1 minus P0 over epsilon, and the total running time is order 1 over epsilon. So this result actually is very similar to the result that Lexing has introduced before, but we essentially achieve it using a different method. Okay, so basically to understand this, So to understand this result, you can see that when my P0 is close to 1, actually my Tmax can be much smaller than pi over epsilon. Okay. Yeah. So Okay. So then, so we can also understand this result from this graph. So here, if we try to let this delta to be the pre-constant before 1 over epsilon in my T max, then if we look at all the QP type method, then for any P0, this delta is always larger than pi. Okay, so from 0.5 to 1, it's always larger than pi. But for the Hadamard test, you directly drop to 0. Okay, so
what is delta?
And delta is a pre-constant before 1 over epsilon in your Tmax. Yeah. So okay. So then in our first paper, we try to produce this orange line, which kind of interpolate between this blue line and this red point. So here I want to mention that we can only achieve square root of 1 minus p0 over epsilon in our first paper, which is the orange line. But maybe like 1 month later, we find our analysis is not optimal. We can further improve it to 1 minus p0 or the epsilon, and we write it in our second paper, which is the green line here. So basically, our method can interpolate between this blue line and this red dot. Okay. So we also have some numerical evidence, and the more interesting thing is, according to our theoretical result, we can only achieve shorter circuit depth when my p0 is closer to 1. However, according to the numerical result, the situation is even better. So here you can see in our numerical result, even my p0 is closer to 0.6. We can still achieve a much smaller circuit depth compared with QPE. So it's actually 2 orders of magnitude reduction of the maximum running time. And on the same time, the total running time of our method is still slightly smaller than QPE. Okay? Yeah, okay. So now the algorithm. So actually, I think one good thing about QCELS is its algorithm is actually very simple. So basically, there are 3 steps in our algorithm, and only the second step involves the quantum computer. So in the first step, I try to draw some random samples Tn from a truncated the Gaussian distribution. You can essentially understand it as we draw from Gaussian distribution. Here, I do the truncation, because I want to make my Tmax to be finite. Okay, then in the step 2, I put this Tn into the quantum computer and generate bunch of signal Ct. And the interesting thing is here, for each Tn, I only need to generate 1 sample. Okay, then after I generate this sample, I formulate this optimization problem. So basically, I define my optimization problem in this way. So one intuitive way to understand it here is, you can imagine this Ct is a signal. Then I only use a single signal, which is R exponential I theta Tn to fit the original signal. And by solving this optimization problem, I can output my theta star, which is an approximation to lambda 0. So this is our algorithm. Okay, so any question here?
Sorry. Is there any lower bound for the Tmax?
Yes. So I believe that's depend on So I think that's dependent on different cases, but in some sense, the 1 minus p0 over epsilon is kind of optimal. And another optimal lower bound is 1 over delta, where delta is the spectral gap between lambda 1 and lambda 0. Yeah, so it highly depends on your assumptions. Yeah, but we do have some lower bound. So actually, classically, people can prove some lower bound. Okay. So now, our rough algorithm can be summarized into the following picture. Essentially, we have a Hadamard test circuit. We generate some signal, put it into the classical computer, do QCELS, do the fitting, then output lambda 0. Okay, so intuitively, one way to understand our algorithm is, so here, although we only use one sample for my CT, but since its expectation equals to this signal, then you can kind of understand, so you can kind of imagine CT is closer to this signal, then the important part is, since this P0 is larger than 0.5, then to make my single signal can fit this multiple signal, the optimal choice should be my theta star should be closer to lambda 0. So this is the intuitive way. Okay, so now I want to give a proof for why our methods work. Okay, so essentially, essentially, I want to show that by solving this optimization problem, how I can achieve this short circuit depth. So here, one thing I want to remind you is here, how we define this Tmax. This Tmax is actually the max of Tn, and since we are doing the truncated Gaussian, it's always bounded by gamma times capital T. Okay, so then in the informal proof, to consider this optimization problem, we first need to study what this optimization problem is doing. Okay, so here, for simplicity, I just assume that I have enough number of samples. My capital N is very large. Then we recall that my Tn is RID sampled from AT. Then basically, by doing some calculation, we can show that if I let capital N go to infinity, the solutions of this optimization problem will be very closer to the solutions of this optimization problem. Here, I replace this CT by its expectation, and I replace this summation by this integral. Okay, so then the second step is I can pick out this as exponential minus I theta t and put it into this CT part and change it into this form. Then, if you look at this formula, the interesting thing is it's a quadratic function with respect to R. So essentially, for any fixed theta, if we want to optimize R, we do have a closed formula. And for any fixed theta, we can solve this R, and we can plug into this formula and reformulate this optimization problem. So essentially, by doing in all of the above calculation, I can reformulate the optimization problem into a max problem. So basically, the solutions of this optimization problem is equivalent to this part. Okay, so here we do have some complicated formula, but it's actually not very complicated.
Can you remind me what is AT?
Yeah, so AT is some Gaussian function. Yeah.
Oh, yeah.
Yeah, some Gaussian distribution. Okay. Yeah. Okay. Okay. So now we want to solve this optimization problem. What can this tell us? So basically, if you look at this part is essentially it's very similar to the Fourier transform. So here, it's actually called the inverse Fourier transform. So if I try to define the function capital Fx in this way, then I can essentially replace this part by a summation part. Here this capital F is defined by this inverse Fourier transform. Okay, so then the interesting thing is if I define my AT to be a truncated Gaussian or Gaussian function, and I choose my gamma to be some order the one parameter, then I can show that my capital Fx also has a Gaussian form. Okay, my capital Fx will be approximate to exponential minus t square x square over 2. Okay, and if you try to draw this Gaussian function, it's a highly concentrated function centered around x equals to 0. And the important thing is the width of this peak is proportional to 1 over capital T. Okay, so we kind of build a Gaussian filter function. Okay, so now if you replace this fx by this exponential part, I can change my loss functions into the following formula. So basically, here you have some exponential filter function. And if you try to draw the landscape of this loss function according to theta, it will basically be something like this. So you will see a lot of peaks, and for each of the peak, it actually corresponding to one eigenvalue. Okay, and here the important thing is, since I chose my p0 to be larger than 0.5, so we always have the largest peak around lambda 0. So if I maximize this loss function, my theta star will be always closer to lambda 0. And since previously, so I have told you that the width of the peak is order 1 over capital T. So here, so according to this graph in the first step, we can at least show that my theta star minus lambda 0 absolute value is bounded by some constant c over capital T. Yeah. So this is essentially our first step. So at least we can show that this T max is equals to c over epsilon. Okay. So now I want to refine this constant c. So how to show that this constant c is much smaller than 1? To do this, we need to zoom in this highest peak and try to study closely what will happen when my p0 is closer to 1. Okay, so.
Question. So here you want to get a deterministic bound for T max, right?
Yeah.
For the truncation. But what if you took a more like a randomized algorithm view? You say I only want the T max to be bounded by a number with high probability.
Oh yeah.
And then you don't need all these truncations.
Right. So you I think without the truncation, you can exactly you can get exactly the same result also with high probability. Yeah, that's true. Yeah. Okay. So then in our second step, how to make my constant c to be small. So first, I want to do some approximation. So actually, it's not approximation. I can reformulate my loss functions into two terms. I pick out the ground state energy term and plus some arrow. So one thing you can notice that since this exponential part is always smaller than 1, then the absolute value of this arrow term is always bounded by 1 minus p0. This meaning that if my p0 is very close to 1, this arrow term is actually very small. Then I only want to focus on the regime where theta is closer to lambda 0. Okay? So now, in the case 1 p0 equals to 1, this essentially means that we don't have this arrow term. And if I try to draw the landscape of my loss function, you only have a single peak. And then the maximum value, the maximum point of this loss function is exactly at theta star equals to lambda 0, right? So for this case, we will get an exact solution without any arrow. So now, if my p0 is closer to 1, then basically in my loss function, you can see this red line. We will have some other peaks, and also the effect of this other peaks to this largest peak is it will try to move the maximum value to the right-hand side. Okay. However, since our arrow is always bounded by 1 minus p0, so by doing some calculation, we can show that the effect of this arrow term can be bounded by 1 minus the p0 over capital T. Okay, so essentially this green distance is bounded by 1 minus p0 over capital T, and that's how we get. Our T max is order 1 minus p0 over epsilon. Yeah. So any question here? Okay. Yeah. Okay. So now we go back to our informal theorem. So previously we have already shown that our T max can be 1 minus p0 over the epsilon. So but to show the Heisenberg limiting scaling, it will be a little tricky and involve like a complicated calculation. So basically, to show our algorithm can achieve the Heisenberg limited scaling, we kind of need to uniformly bound the effect of the random arrow in CT for all theta. So we kind of need to use a uniformly bound, and theoretically, it's not very easy. Okay, so to be honest, theoretically, if you if you want to show that our rough algorithm can directly achieve the Heisenberg limited scaling, it's actually very hard. Very hard because of some technical problem. Okay, so in our paper, we try to write a little more complicated algorithm, which is instead of using one capital T, we try to choose an increasing sequence of Tn, which equals to 2 to the nth power times T0. So we gradually increase our capital T and refine our estimation. Okay, but but I want to emphasize that I believe this is just because a technical problem in our theoretical analysis. So in the real application, you only need to run it with one capital T, and the algorithm will always succeed. Okay, and another fix to this theorem.
So when you say to achieve local absolute scale, you need multi-level, but the one without multi-level also achieve the same scale. Is that correct?
What?
But the one without multi-level, does it also achieve the Heisenberg scale?
No. So to theoretically prove it can achieve the Heisenberg scaling, we do have some technical problem. So in our proof, yeah. So
the version you just described does have a problem.
Yeah. Okay. Yeah. So
the uniform grid is hopeless. With the Gaussian, we believe it's true, but there's some technical things that prevent
What do you mean by uniform grid?
So if the T, you just choose delta T, 2 delta T, 3 delta T,
so
that's
you
definitely not Heisenberg.
choose the T and in this is a hope. So this is a hopeless. You must use a multi-level algorithm to achieve the Heisenberg limited scaling.
I see. Even if you choose Gaussian, is because the noise in the randomness that's going to destroy the optimization problem?
No.
What will fail in your analysis? I mean,
Yeah.
do the more stochastic kind of analysis.
Right. So that's essentially go back to this part. I need to bound the effect of the random error for all theta, and because my theta is a continuous variable, you kind of need to bound it a parameterized random variable for all theta. So it's theoretically it's a little hard. Okay. Yeah. But
so you mean that you actually need some chaining arguments and then
yeah.
just have to carry out.
Right. So here another way to fix it is in our optimization problem. Instead of do a continuous optimization problem, I only optimize my theta on some so discrete point. Then we can still achieve this result with one level. So we don't need multiple Tn. Okay, but yeah. So to be honest, I still like the continuous optimization problem because we can do the gradient descent for this optimization problem. We can only do the brute force search. Okay, yeah. Okay. So here I basically finished the first part of my talk, which is about the ground state energy estimation. So yeah. Okay. So now I want to talk about some simple.
It's not just ground state, right?
Yeah.
So from the paper that I read, I think it's a great idea how you fit the spiral into it. But you essentially come out with the mod squared of the discrete Fourier transform. So is there any intuition of why this mod squared of the discrete Fourier transform is better than just taking the standard discrete Fourier transform that Hadamard has signaled?
What do you mean by the multi-squared?
Well, when you solve the optimization problem, it's just a discrete Fourier transform squared.
Oh yeah. So the reason it still says because here in this optimization problem, my theta is a continuous random variable, meaning that my potential candidates for theta is infinite. I kind of need to bound this random error for this infinite candidates. Yeah, so theoretically there is some technical difficulty, but to make it finite, I can always bound it with high probability. Yeah, it's not very hard technically. Yeah, okay. But in real application, I think there is no difference. Okay. Yeah. So let's see.
You were saying that this is for ground state, but it's not.
Right. Okay. So yeah. So we can also easily extend this QCELS to multiple eigenvalue estimation. So here I assume that my initial state have k dominant eigenvalues where I denote it by lambda nk. And I define it to be the dominant eigenvalue, meaning that for each of this nk, the overlap pnk is larger than the summations of the residual overlap. Then our goal is to estimate this lambda nk. Okay, so yeah, so our QCELS can be easily extended to this case. So here, since we want to estimate lambda nk, we basically want to fit multiple signals. Then I only need to modify my QCELS into a multiple variable optimization problem. So here I only need to change this signal part to the k signal part and directly do the fitting. Okay, and we can directly show that it will succeed. So the complexity result will as follows. Yeah. So here I need to define that the gap between the dominant eigenvalues as delta, and also this PD is the summations of the dominant overlaps. Then here in our wall algorithm, we do need to get a theoretical result, we do need our Tmax to be larger than 1 over delta, to be larger than this gap. Then our Tmax still have this 1 minus PD over the minimum of for dominant overlap over epsilon. So one way to understand this result is if PD is closer to 1, we can still achieve short circuit depths. And we still get the Heisenberg limited scaling. And also this algorithm can work as long as the minimum value of pnk is larger than 1 minus PD. Okay, so here why we want to make this Tmax is larger than 1 over delta is essentially because when I try to construct my Gaussian filters, I want to make sure that my capital T is large enough so that different eigenvalues can be separated by different Gaussian filters. Okay, yeah. But in the real application, let's say if I have two dominant eigenvalues which are very close to each other, meaning that this lambda nk plus 1 minus lambda nk is much smaller than epsilon, then what we can do is we can basically see these two eigenvalues as one eigenvalue. Then now in our situation, instead of have capital K eigenvalue, we only have a capital K minus 1 eigenvalue. So I slightly changed my loss function to K minus 1. So we can still solve this optimization problem to find an approximation to all eigenvalues. Yeah, right. So that's the problem with this idea. It's actually not very robust. So priorly, we don't know what is the proper choice of capital K. Yeah. So I think making the algorithm robust is a good direction. Yeah. Okay.
So in practice, are you going to do this one by one?
Or? No. So
what's the reason you cannot do it one by one?
So there are some technical reasons. So I actually tried to think about this, but you will see some technical difficulties in the theoretical proof.
So obvious technical difficulty is that let's say P0 is 0.2, what they're going to do, right? So the previous algorithm works if P0 is bigger than 0.5.
Just pick up whatever the largest and then
to
remain a signal.
Right. But so.
Pure.
No. So this kind of idea does not work because you need to make sure that the minimum of pnk is larger than 1 minus pd. Yeah. So otherwise, you need to choose your Tmax to be larger than every gap between the so each of the eigenvalue to overcome this problem.
Okay. It's not a question about information is theoretic, right? It's a question about how you solve this optimization problem. You can do a pursuit to solve it. It's a non-convex one.
Oh, no.
Do like one by one solution.
No. So actually, what I mean is, even you can find the solution to this optimization problem, it still can't give you a good approximation. Yeah. So.
I mean, let's say that we overestimate k, right? We start for large k. Then what happens is that one of the theta k and theta k plus 1, numerically you get is spurious, right? So they actually correspond to the same thing, so that you can just do a post-processing to merge them.
Right. So, yeah. So I think this is a great idea. Actually, numerically, even we choose this k to be slightly large, numerically we can still see some good result. But how to prove it theoretically, up to now I don't know. Yeah, up to now I don't know.
Do you have an idea what if the gap is like square root of epsilon, or what should be?
Yeah. So that's also a good problem. I don't know. Yeah. To be honest, I don't know. Yeah. Okay. So yeah. So here I can also provide some numerical evidence. So there is some typo in this graph. So basically in this numerical experiment, we still compared with the QPE, and I set this P0 to be 0.4 and P1 to be 0.4. So you can see that. So even in this multiple eigenvalue estimation case, our method can still achieve two order of magnitude reduction of the maximum running time, and the total running time is still comparable. Okay. Yeah. Okay. So yeah. So finally, I want to talk about another application, which is a depolarizing noise.
Maybe worth saying when comparing with the QPE.
Oh yeah.
The QPE only measures one eigen.
Yeah. Right. So here in this experiment, because the QP can only measure the ground state energy, so here the error of QP is only the error of estimated ground state energy. But in this orange line, we actually estimate two eigenvalues and we output the max error. So actually, QP should get some benefit, but still our algorithm is much better than QP. Okay. So last thing I want to talk about is about the depolarizing noise. So here in the previous two projects, we always assume that we have a kind of a perfect quantum computer without any noise. So here, but in this case, we assume that when we apply the Hadamard test circuit, we have some global depolarizing noise. And the effect of this noise is here, when I output my random variable CT, the expectations of CT will have some exponential decay term before this signal, where this alpha is some constant, and this alpha characterizes the strength of this noise. Okay, so then the difficulties of this problem is the following. So assume that we have a good estimations for this alpha. I call it beta, where beta is closer to alpha. Then we can use the error mitigation technique to recover my original signal C beta t. I define it as exponential beta t times CT. Then you can show that the expectations of this C beta t is equals to the original signal. However, the bad thing is if you calculate the variance of this CT, it will be exponentially dependent on beta or like alpha. Okay, this basically meaning that if you intuitively, this means that to overcome this variance and get a good approximation to this expectation, the number of repetitions you need, capital N, is exponentially into beta t. Okay, so why this is not good? Basically, because here, if in this case, we are still looking for the Heisenberg limited scaling, meaning that my Tmax is kind of order 1 over epsilon. And then if I plug this 1 over epsilon into this capital T, the number of repetitions we need is exponential beta over epsilon, kind of exponential alpha over epsilon. Then we can see that the total running time will be exponentially in alpha over epsilon. This essentially means that almost so all the previous Heisenberg limited scaling method is very expensive when we deal with this depolarizing noise. Okay, and we do want to develop some new method to overcome it. Yeah.
Zhiyan, I have a simple question about the setup of this problem. So are you saying that all the qubits are experiencing a depolarizing noise?
Yeah, right.
It's not like one
No.
random. Okay.
Yeah, so I think your case is often called the local depolarizing noise, but for that case, the noise structure is very complicated. Yeah. So. Okay. So. Yeah. Okay. So then, basically, you can see to overcome this exponential blow up effect, we do need to find an algorithm such that my Tmax is order log 1 over epsilon. And in Peter's talk, you already see one algorithm that can achieve this. Okay, and here we can show that our QCELS can also achieve this by free. Yeah. So basically, if I define the spectral gap delta between lambda 1. So equals to lambda 1 minus lambda 0. And I assume that I already get a good estimations for the parameter alpha, where my beta minus alpha is absolute value, is all the epsilon. Then I only need to run QCELS with a Tmax equals to 1 over delta log 1 over epsilon. And on the same time, the total running time is 1 over epsilon alpha over delta plus 2. So although this is a relative large power, it's not exponential. So for high precision epsilon, it's still polynomial. So here, I think one thing I can say for sure is when we deal with this depolarizing noise, there is no hope to get the Heisenberg limited scaling because your Tmax cannot be 1 over epsilon. Okay? Yeah. So basically, I think the best result we can hope for is something like 1 over epsilon to the square. Okay, but how to get the 1 over epsilon to the square? We still don't know up to now. Okay.
You mean the lower bound for T total, not Tmax?
Yeah, right. So if you want to get the Heisenberg limited the scaling, so your Tmax must be order 1 over epsilon. Then by the previous analysis, you cannot get like T total to be 1 over epsilon, right? Okay. So then the noisy QCELS is actually very simple. So we already have an estimations for alpha. Then we basically I will mitigate my previous signal CT, and I still solve this optimization problem, and we can directly show this result. Okay, so now I want to show another intuitive proof to show that why we can achieve even smaller Tmax. Okay, so here previously in my previous analysis, I tried to bound this arrow by 1 minus p0, and this make this constant to be 1 minus p0. However, actually, if my capital T is larger than 1 over delta, we can find a better bound for this arrow term, which is exponential minus t squared delta squared over 2. Then you can imagine this as the previous 1 minus p0. Then I can put this term into this arrow bound. So essentially, the arrow can be bounded by this exponential decay term over capital T. And this is essentially how we show our Tmax can be 1 over delta log 1 over epsilon. Okay? Yeah, so any question about this part? Okay.
You mean P0 is greater than 1 over delta or 1?
Yeah, so no. So sorry. So this P0 is larger than 0.5. Yeah, so there is a typo here. Yeah, sorry. Okay. Yeah, it's a typo. Okay. So now, so I want to give some conclusions. So basically, in in my talk, I told you that to do this quantum phase estimation, if we use the Hadamard test circuit, we can translate it into a signal processing problem. So essentially a classical problem. Then here in my talk, I try to use the QCELS to solve it, and I have shown that this QCELS is a very robust method. It can do the ground state energy estimation, do the multiple eigenvalue estimation, and also deal with the depolarizing noise. Okay, yeah. And also, I want to emphasize in this field there are also other signal processing methods, and actually there are some recent papers also consider how to do the post-processing for the signal, and I think most of the authors of these papers are in IPAM. So if you are interested, you can also discuss with them. Okay, yeah. So finally, these are the three papers I introduced today, and yeah, I welcome questions.